What is learning from label proportions? In general classification tasks, a model is trained on dataset where each piece of data has class labels. However, instance level annotations cost a lot, and there are many cases in which instance level annotation cannot be disclosed to the public for privacy reasons. In such a situation, we only know the label proportions given to a bug and must train a model from these label proportions to classify each instance. The training data is label proportions, but we must train a model from these label proportions to classify each instance. During test time, it is required to classify each individual instance. This problem setting is known as learning from label proportions, LLP. Different from supervised learning, LLP is a training task. Here we checked how the number of bugs affects accuracy. We increased the number of bugs as shown in left image. When we generate new bugs, we use given instances. Therefore, in this situation, the total number of instances is fixed. As a result, we observed that the accuracy improved as the number of bugs increased, even though the total number of instances is fixed. Following the preliminary experiments, we proposed a bug-level data augmentation called MixBag. To the best of our knowledge, there are no prior studies of proposing bug-level data augmentation. In our methods, we randomly choose two bugs and sample some instances from them. The set of sample instances is called subbug. We mix two subbugs to generate new bug. Here, we can increase the number of bugs by applying MixBag. But we can know the true label proportion of generated bug. So we also developed confidence interval loss. The proportion of bug generated by MixBag is unknown. So we estimate the deviation of label proportion using confidence interval, which is well known in statistics. We can determine the approximate label proportions of bugs generated by MixBag. We also determine the confidence interval shown in right figure. The true proportion is in the range of confidence interval with high probability. The CI loss ignores the loss when the estimated proportion PCI is in the confidence interval, since gaps in the CI often occur. Please focus on the figure on the right. If the estimated proportion is in the confidence interval, the loss function does not be applied. However, if the estimated proportion is out of the CI, the loss function be applied. Experiments. We introduce our method with three existing methods. In all current LLP methods, MixBag improved accuracy from baselines. From these experiments, we could observe that our MixBag can be applied to any LLP methods. We introduced MixBag with instance-level augmentations. We used standard augmentation techniques: flip, erase, invert, Gaussian blur, and perspective. From the table, we can observe that instance-level data augmentation improved accuracy. But our methods further improved accuracies by combining with instance-level data augmentation.